over h bar over 1 e minus e n. So this is just counting one subband. Okay, there are many subbands. If I just plot E as a function of kz again, okay, I have one subband. I can have many subbands, just like the previous case before. And then if I were to match up the subband, whenever I see this thing, this mapping of density of states gives me a compression. The compression is essentially what causes the singularity. There's no more expansions like before. It was a compression and expansion there, but here they were just compressing the density of states from the K space to the E space. And then as you match up, you pick up the singularities more and more. So if you were to plot this as a function of E, okay, it will look something like this. That you plot E and then you plot the density of state, then there's nothing there, and then you will have a singularity for the first subband, and then the second subband you might have a singularity. So you get this spike for quantum Y. Okay, so the density of states looks something like that. Okay? And then it looks something like that if you make the thing larger and larger. Have some of this plus in the thing. Okay, there's another thing that I wanted to talk about, but I didn't have time to talk about. So just let me tell you what it is. It turns out that if you have a quantum wire, say if you have a quantum wire, and if you want to measure the resistance, okay, of this wire, and it turns out that the resistance does not become vanishingly small if you make the L smaller and smaller. This is quantum wire. You have confinement in the x and y direction, but you just want to measure the resistance in this direction by, say, making contact 1 and then contact 2. Okay? It turns out that the resistance, like according to Ohm's law, the conductance G goes as 1 over L, according to Ohm's law. And G tends to infinity when L tends to 0. This is according to Ohm's law. But according to quantum mechanics, that doesn't happen. G tends to a constant when L tends to 0. This is quantum mechanics. Okay. The reason is because in Ohm's law they are collision limited transport. Okay, the shorter the length you make it, the less collision there will be. Eventually the conductance goes up. This is the conductance. But in quantum mechanics, it turns out that if you make the length smaller and smaller, the conductance doesn't go up indefinitely. The reason is because when you make the length smaller and smaller, the number of modes that you have available for transport, for electronic transport, becomes less and less. The density of states, you can say in the z direction, we have confinement in the x and the y direction, but if you make it shorter and shorter, there will be less and less modes you can have between these two terminals for electron transport. Okay, even though because of that, you actually have this tending to a constant. That value is actually quite interesting value. It's q squared over g is equal to q squared over h bar. Okay, or h, just h. So it's entirely a quantum mechanics effect. It's actually written up in Dapta's book. Okay. So this is entirely a QM effect. And so if h goes to 0, you get infinity again. If h goes to 0, then quantum mechanics disappears. You have this number going to infinity. So this is something that you should be aware of, that if you make transistors smaller and smaller, doesn't mean that you can transport the electron across the transistor easier and easier. It actually has a finite value due to wave physics. Okay. Okay, I guess Ayin will lecture next time. Come to class.